right, for number 1 on the formative assessment, I have y is equal to negative 2 to the x power. For this, my parent function is y is equal to 2 to the x power. The table that I'm going to have is negative 1. There's no horizontal shift, so I don't need to move my x values to the left to leave any space for anything. I have negative 1 and 0.5. I have 0 and 1, and I have 1 and 2. From there, I know that the only transformation or extra thing that I see besides 2 to the x power is that negative in front. That tells me that I'm going to multiply all y's by negative 1. I'm going to multiply all y's by negative 1. That's what actually happens to my parent function points when I'm doing a reflection over the x-axis. So I'm multiplying all of these by negative 1. And when I do that, they just change to their opposites. So my new table will be negative 1 and negative 0.5, and 0 and negative 1, and 1 and negative 2. And that will be, for the function, negative 2 to the x power. My asymptote for that is, there is no vertical shift. I'm not adding or subtracting anything, so the asymptote is automatically at y is equal to 0. The y-intercept I find by plugging in x is equal to 0. So when I do that, I get y is equal to negative 2 to the 0th power. That is, y is equal to 2 to the 0th power is 1. And then I have negative 1. So it is 0, negative 1. Domain is negative infinity to positive infinity, always. I'm going to graph to see for the range, but first I'm going to plot my horizontal asymptote. And that's y is equal to 0. And then I'm going to plot these points. So I have negative 1 and negative 0.5. I have 0 and negative 1, and I have 1 and negative 2. I'm going to connect these, making sure I approach but don't touch the x-axis. And then I can see that my lowest y value for the range is negative infinity. And then my highest value, I can't actually write it, but I can say what it's approaching. It's approaching 0, so I'm going to use 0 to be the last number in my interval. And I'm going to put a parentheses on it to indicate that everything just a little bit less than 0 is included, but 0 is not. So I'm getting closer and closer to 0, but I'm never actually going to get y is equal to 0. And that's the graph for the first problem. For the second problem, I have y is equal to 4 times 1/2 to the x power. So my parent function in this case is y is equal to 1/2 to the x power. And I'm going to use negative 1, 0, and 1. I don't have any horizontal shifts, so I don't need to move my x value to the left at all. For y, when I plug in negative 1, I'm going to get 2. When I plug in 0, I'm going to get 1. And when I plug in 1, I'm going to get 0.5. And then the only transformation that I see is this 4 in front. When I see a coefficient, that means that I have a vertical stretch. And what's actually happening is my y values are changing when I have a vertical stretch. They're multiplying by 2. So, sorry, in this case, 4. I don't know why I said 2. So I'm multiplying all of my y values. So this means I multiply all y values by 4, that coefficient. So I'm multiplying all my y values by 4. That's the only transformation happening. That's going to give me y is equal to 4 times 1/2 to the x power. This multiplying by 4 gives me this coefficient. And then the table for that new function is going to be negative 1, 8, 0, and 4, and 1, and... Wait. Oh, that's a 0.5. That was like 20. That's crazy. 4 times 0.5, which gives me 2. And then I plot these points. Well, first I'm going to talk about what's the horizontal asymptote. I had no vertical change, so it's automatically at y is equal to 0. I'm going to draw that. Y is equal to 0 is my horizontal asymptote. I'm going to plot these points. So I have negative 1, 8. I have 0 and 4. And I have 1 and 2. And I'm going to connect these, making sure I approach but don't touch that horizontal asymptote. The y-intercept is when x is equal to 0. I have that point. It's 0, 4. I have the domain is always going to be, all my x values are included, negative infinity to positive infinity. And then the range is, I can see I'm starting at 0 and going to positive infinity. I'm never going to actually touch 0, so I put a parentheses on it. For number 3, I have the parent function. So the parent is going to be y is equal to 3 to the x power. I have stuff happening to my x since I see stuff in the exponent extra. So I'm going to move my x values a little bit to the left to leave enough space for my transformation. I have -1 and 0.3. I'm going to round. 0 and 1 and 1 and 3 for that parent function. To that parent function, the transformations that I see, one thing that I see is this +2 in the exponent. That means that I'm moving left 2. I'm moving all points left 2. And when I move left, that's affecting my x values. It's affecting my x values by I'm subtracting from them, and I'm subtracting 2, in this case, from all x's. This -1 on the outside or at the end tells me that I am going, every point is moving down 1. Every point is moving down 1. So I'm going to subtract 1 from all y's, because if I'm moving vertically, my y's are being affected. I have the last transformation I see is this plus this 2 in front. That 2 in front tells me that I multiply all, it's a vertical stretch, and I multiply all y values by 2. And so I'm going to do all of this. I'm going to start with my x's. I am subtracting 2 from all of them. That takes care of this transformation. The second transformation that I see that I wrote is down 1, which means I'm subtracting 1 from all my y values. But I have to be careful because there's 2 different things happening to the y values, 2 transformations, and I need to make sure I'm doing them in the order of operations. So I'm doing this one first, multiply all y values by 2. And then after I do that, I can do this transformation of moving them all down 1. So subtract 1. And with these shifts, I will end up with y is equal to 2 times 3 to the x plus 2 power minus 1, which is what I want. And the new points will be -3 and -0.4. I have -2 and 2 minus 1. And the last point is going to be, I have -1 and 5. And before I plot these, my horizontal asymptote, I have a shift of down. I'm moving everything down 1, so it's going to be at y is equal to -1. That's my horizontal asymptote. I plot these points, making sure I don't touch that. -3 and -0.4. 3 and -0.4. I have -2 and 1. And I have -1 and 5. 1, 2, 3, 4, 5. Right here. And then I connect them, making sure that I approach but don't touch that horizontal asymptote. The horizontal asymptote is -1. My y-intercept I find by, it's not one of the values here, so I need to plug in 0 for x and see what I get for y. That's how I always find my y-intercept. I do y is equal to 2 times 3 to the 0 plus 2 power minus 1. 3 to the 0 plus 2 power is 3 to the second power. That's 9, so I have 9 times 2 minus 1. 18 minus 1 gives me 17. So it's 0, 17 is my y-intercept. The domain is always the same, negative for exponential functions, -infinity to +infinity. There's no value for x I can't plug into the exponent. And then the range is going to be, in this case, -1. Oops. I have -1 to +infinity. That -1 comes from the fact that this is my horizontal asymptote. All right, for number 4, since 1910, the panda population has been decreasing exponentially, and by plotting a decay curve, scientists are in a better position to predict and plan for the future. In 1913, the panda population was 0.25 million, and in 1915, it was 0.0625 million. Taking 1910 as the starting point, I want to know what exponential function could we use to predict how many pandas there would be in 1925. So I don't actually have to calculate how many pandas there would be in 1925. I just want to know what equation I would use. What I have been given here is, I haven't been given, well, first of all, before I start, I want to talk about what formula am I going to use for this. I do not see the word compounded, so I know that I'm using the exponential function since this is an exponential situation, exponential growth situation. I'm using y is equal to a times b to the x power. That's what I'm going to use. I don't know what A is, and I don't know what B is. I don't have those values. I'm just going to move this to the side. I don't have A and I don't have B. I need to figure out what they are. And if I'm missing two variables, the only way I can solve for those variables is if I create a system of equations to solve. I need two equations to solve if I'm missing two variables. So what I've actually been given in this case is two ordered pairs. The first ordered pair that I was given was, in 1913, the population was 0.25 million. I know that the start is 1910. My x value is always, in these problems, going to represent how many years have passed by. How many time periods have passed by, I should say. And in this case, we're going to say every time period is 1 year. How many time periods have passed by? Let's just say how much time has passed by. How much time has passed? And then y is going to represent what the population is. Or let's say the new population. Okay, so for this ordered pair, the ordered pair that's actually been given to me, if I write ordered pairs x, y, my input would be 3 years have passed by, and the population would be 0.25 million. I'm going to ignore the million, and whatever equation I write, I'm just going to note that the answer is going to be a million. So this is the first ordered pair that I have. The second ordered pair that I have is in 1950, I know the population. So I have an x and y value that go together. Well, that's not my x value. Be careful, your x value is 1915. It's how many years have passed by since 1910. And that is 5 years. So 5 years have passed by, and the population is 0.0625. So I have these 2 points now. What I'm going to do when I create this system of equations, I know that I'm going to have to divide the two equations to cancel out one of my variables, because I need to cancel out one of my variables in the system for me to be able to solve, since I can only solve a one variable equation. I know I'm going to be dividing. I want the bigger x value to be the equation on top that I am going to divide the other equation from. So I want the lower exponent to be on the bottom, or to be the thing that I'm dividing by, because I want a positive coefficient for b when I do that division on the right hand side. So I'm actually going to put this equation on top, and all I'm going to do is I'm going to plug in this x and y value into this general form. So y is 0.0625, and I have a times b, I don't know what those are, to the x is 5, the fifth power. For this second point, I'm going to have 0.25 is equal to a times b to the third power. I just plugged in that x and y value, and now I have this system of equations. What I'm going to do is I'm going to, I want to cancel out one of my variables. I can very easily do that on the right-hand side by dividing the top equation by the bottom equation. So I'm going to divide these two equations, and these a's are going to cancel out. On the right, I'm going to have b to the fifth power divided by b to the third power instead of b to the third power divided by b to the fifth power. I know when I do that, I'm going to have b to the 5 minus 3 power instead of 3 minus 5. So I'm not going to have a negative exponent, which is going to make my life easier. I'm going to have b to the second power is equal to 0.0625 divided by 0.25 is 0.25. To find b by itself, I'm going to take the square root of both sides, and I'm going to see that b is equal to 0.5. So this is my growth rate, and I'm going to use this growth rate to find what my initial amount is. I'm going to plug it into one of my equations. It doesn't matter which one I pick for a system of equations, the answer is going to be the same. So I'm going to pick the one with the smaller numbers. 0.25 is equal to a times b to the third power, and I'm going to plug in 0.5. So I have 0.25 is equal to a times 0.5 to the third power. 0.5 to the third power gives me 0.125. So I have 0.125 times a gives me 0.25. I'm going to divide by 0.125 on both sides. And when I do that, I'm going to end up with, I don't know why I put that in parentheses. I'm going to end up with a is equal to 2. So now a is 2. This is my initial amount. and I'm multiplying, the growth rate is 0.5. So I have y is equal to 2 times 0.5 to the x power. And this is going to tell me x is the number of years that have passed by since 1910. And y is the population in millions. And that's my answer. I'm going to erase that bubble so I can not have the so I can see what my fifth problem says. Cesium has a half-life of 30 years. You make 20 grams in chemistry class. When you come back later to your class reunion 50 years later, I want to know how much is left. For the previous problem, we could create our own equations. So we made the growth rate applied every year. So we could find the annual rate of what was going on. Or that's what we really wanted for that problem. Every year, what's the growth rate? That's what we were looking for. For this problem, it says that the growth rate is being applied not every 1 unit, not every 1 year, but every 30 years. So every 30 years. And I'm going to have to keep that in mind when I'm doing this equation. Since I don't see compounded, I know I'm using y is equal to a times b to the x power for this exponential growth problem. I know I need to know a, which is the initial amount. So the initial amount. And the initial amount here is going to be 20 grams. That's what I started with, 20 grams. The growth rate, or b, in this case, is given to me in the problem. I don't need to calculate it. It's telling me that it's halving every 30 years. It's cutting in half. So the growth rate is 1/2. I multiply by 1/2 or divide by 2 is what that also means. The other thing that I have to keep in mind is this is the time period. So this is how long a time period is. This is how many years before that growth rate is applied, or every 30 years that growth rate is applied. So I need to keep in mind that the time period is actually 30 years. When I create this problem, I have y is equal to 20, the initial amount, times my growth rate, 1/2, raised to the x power. This exponent actually means the number of time periods that have passed by. So time periods that have passed by. And that's usually one year, or 1 unit, number of time periods that have passed by. But in this case, it's actually every 30 years. So if I want to plug in for x a number of years, I'm going to have to divide that number of years by the time period to see how many time periods I actually have. In this case, I have 50 years are passing by. So I'm going to do y is equal to 20 times 1/2 to the 50 divided by 30 power. 50 divided by 30 tells me I have 1.66667 time periods that have passed by. So I'm doing 20 times 1/2 to the 1.666 repeating power, and that's going to give me an answer of 6.30 grams when I round. For number 6, your new house depreciates at 23% per year. If your house is worth $100,000 after you've owned it for 5 years, what was it originally worth? What's important here, first of all, I know that I'm not using, this is money, but I'm not using compound interest. I don't see the word compounded. I'm not talking about a bank account giving me interest. And I'm also depreciating. That doesn't happen for compound interest. So I'm using the formula again, y is equal to a times b to the x power. In this case, I'm going to need my initial amount. The initial amount is going to be, I don't have it. So I don't know what the initial amount is. I'm going to need to, that's the missing variable that I need to solve for. So what I actually have been given, if your house is worth $100,000, $100,000 after you've owned it for 5 years. So this is the end amount. That's the final amount. I know that is going to be my y value, what I'm plugging in for y. So this is 100,000. I know I'm missing a, so I need to solve for what a is. B in this case is, so my growth rate is going to be 23%, but it's depreciating at 23%. So I have 1 minus 0.23 is what B is equal to. So it's 0.77. I'm going to plug that in, and then I have the number of years that have passed by, so x is equal to 5. I'm going to plug in 5. I have 0.77 to the fifth power is 0.27067844157 times a, which gives me 100,000. I'm going to divide both sides by this number, so 0.27067. Hopefully you have a calculator that can you have a second answer button, so you don't have to write all those decimals out. And then the original amount of the house was $369,442.09. If you round to, actually, I think it's 10 cents. Is it 10 cents? Let me check. 0.77 to the fifth power. And I'm going to take 100,000. And I'm going to divide by that. Nope, it's 9 cents. Should be 9 cents. All right, for number 7, I have if $4,200 is invested in a bank account, For number 7, if $4,200 is invested in a bank account paying 7% interest compounded continuously, how much will be in the account at the end of 4 years? First of all, this says compounded. This says compounded, so I know it's a compound interest formula that I'm going to use. It says compounded continuously. So I know I'm using A is equal to P times E to the RT power. That's the compound interest formula I'm going to use. P, in this case, that's my principal amount, is $4,200. Be careful deciding if the cash that's been given to you is the amount invested or the principal, the original amount, or if it is the final amount. In this case, it's the cash that was given to us was the principal, the investment. And the rate is 7%. It's 7%, so I convert that to decimal form, 0.07. I just need T, which is 4 years. 4 years have passed by, and I'm just going to plug these numbers in. So I have A is equal to 4,200 times E to the 0.07 times 4 power. And that gives me A is equal to 4,200 times E to the 0.28 power. I do E to the 0.28 power in my calculator, then multiply by 4,200, and I'm going to end up with $5,557.15. For the last problem, I have you deposit $5,000 into an account paying 8.25% annual interest compounded semi-annually. This says compounded semi-annually, so I know I'm using the other compound interest formula. Well, I know I'm using a compound interest formula because it says compounded, and I'm using this one, A is equal to P times 1 plus R over N to the NT power, because it says it's compounded a specific number of times per year. The initial investment was what was given to me, $5,000 I deposited into an account. If it says deposit, if it says initial, if it says investment, it's my principal. Principal is, in this case, $5,000. The interest rate is 8.25%, so I know I'm going to convert that to percent by just moving the decimal point over 2 times, because really what percent means is out of 100. So this is 8.25 over 100, which just means I'm dividing by 100, moving the decimal point 2 to the left. I need N in this case, and N is semi-annually means half a year. Every half of a year, that's 2 times per year, so N is equal to 2 times that it's compounded per year. Do not put 1/2. And then the T is the amount of years is 10 years that have passed by. So I plug this all in. I have A is equal to 5,000, times 1 plus, I have 0.0825 divided by 2 raised to the 2 times 10 power, or that is the 20th power. 2 times 10 is 20. I do 0.0825 in my calculator. Divide by 2. From that number, I add 1. I take that number and I raise it to the 20th power. I take that number and I multiply by 5,000. And I get, hopefully you have a calculator that can hold answers for you. And I have $11,222 exactly when I round to the nearest hundredths place.